Hello there, good morning or good afternoon, wherever you are, and welcome to today's Telecoms.com intelligence webinar produced in association with Corning. My name is Tim Skinner, and I'm the content manager for the Telecoms.com intelligence series. Today's webinar will be looking at the future of broadband access, considering fibre rollouts as means for accelerating access speeds, maximising capacity, and managing rapidly growing data consumption. Telecoms operators are increasingly being forced into re-evaluating network infrastructure to accommodate the boom in data consumption brought on through the proliferation of connected devices. The space constraints that are regularly encountered in the access network has been a key driving force behind cable innovation, and new, lightweight products that are easier to install and extend the life of existing infrastructure are emerging. We'll be looking at some of the challenges that lead to the design of 200 micrometer fibre cables. We'll look at compatibility considerations with existing infrastructure, the benefits new fibre presents to the network lifespan, and how it's possible to extend the data capacity through upgrade paths. Joining me today is Ian Davis from fibre specialist Corning. Ian's been at Corning since 1989, where he's been responsible for various roles focusing on product engineering, cable maker technical support, and product testing throughout Europe. He's also taken on responsibility for defining and executing the product strategy for Corning's single-mode fibre products and subsequently high data rate fibre products. He's currently the regional marketing manager for EMEA at the firm. Without doubt, you're in great hands for today's presentation with Ian at the helm. At the end of the webinar, we'll have some time for Q&A with Ian. You can submit a question for him at any time during the presentation. Simply type your comment into the dialog box that you can see on this page. Responses will appear at the end of the presentation. So, without any further ado, Ian, hi. Thanks very much for joining us today. The stage is yours.
Thank you, Tim. Hello, my name's Ian Davis, and I'm the Regional Marketing Manager for Corning's optical fibre products in EMEA. Thank you for taking the time to listen to this talk today, where I plan to discuss some of the challenges that are being faced by telecoms operators with their access network infrastructure. And I want to talk about the important part played by a new class of smaller, bend-resistant optical fibre products that can ensure the constrained space found in access networks can be filled more efficiently. The primary focus of optical fibre installations today has shifted to the access as operators look to upgrade the infrastructure to support the voracious needs of their customers to consume data. This data consumption seems destined to follow a virtuous circle of growth. To begin with, the availability of data-rich applications, primarily video and including user-generated content, creates a compelling desire from customers to want to subscribe to a high-speed broadband package. As prices of internet-connectable devices and subscriptions continue to decline, the proportion of the public that can afford a high-speed connection increases. And those houses with a high-speed connection tend to access the internet with more devices simultaneously. For example, whilst mum and dad stream a movie to the TV in one room, children can be researching homework or browsing YouTube videos on tablets in other rooms. A recent survey found that there's an average of 6 connected devices per internet household in the US. And remember, these devices can be both creating content and consuming bandwidth. And so the need for access networks that can cope with a torrent of data grows and grows. We can see from this survey of bandwidth consumption in the US that the dominant applications employ video streaming, driving the need for improved connections and robust access infrastructure. In the future comes the so-called Internet of Things. That is, numerous everyday objects, such as sensors, connected wirelessly to the Internet and transmitting continuous streams of data. This will only add to the pressure on operators striving to maintain outstanding quality of service. When planning to upgrade the access infrastructure, operators must consider a number of different needs, not all of which point in the same direction. Firstly, longevity. The fibre plant can be expected to remain operational for decades. In the future, higher data rate protocols will be required for which the fibre needs to remain compatible. These are likely to rely on transmission at longer wavelengths where macrobending losses induced by tight turns can be more severe. Another consideration is compatibility with the existing network. As far as possible, the fibre selected should have the same optical attributes to the fibre that's already installed, most probably legacy G.652D fibre with a 9.2 micron mode field diameter. it should also be suitable for use in other network segments, such as the long haul and access. Next comes performance. A fibre that maximises the area of coverage is desirable, as is one that can support higher data rates with minimum network redesign. And finally, in the access, miniaturization is vital. Smaller cable designs provide, as we will see, opportunity for faster, cheaper installation, getting subscribers online more quickly in order to monetize the new assets. In the access, space is at a premium, and the crowded network infrastructure can be limiting. Unless innovative ways are found to install large amounts of fibre in the limited space available, operators will be forced to dig new trenches and install new duct to upgrade capability. This can add considerably to the upfront costs of the project. In order to maximise the use of the duct infrastructure, the industry has progressively been reducing the size of both ducts and cables over the years. Now ducts are commonly subdivided into smaller microducts in which cables are either pulled or blown. To progress this further, a new generation of single-mode fibres with smaller coating diameter has been developed to allow tighter packing densities while still meeting industry-required cable performance. This new class of optical fibre comes with a reduced coating diameter from typically around 242 microns to 200 microns. The glass diameter is unchanged, 125 microns, ensuring that equipment and processes for splicing and connectorization activities remain unaffected. The thinner coating enables around 30% reduction in the cross-sectional area of each fibre. Consider a conventional stranded loose tube cable of 96 fibres. This consists of 8 tubes of 12 fibres each, stranded around a central strength member. The smaller occupation of the 200 micron fibre allows smaller tubes to be constructed, and so more tubes can be stranded together. An increase in the fibre count from 96 to 144 fibres in the same space becomes feasible. Alternatively, the smaller tubes can be stranded around a smaller central strength member, allowing the 96 fibre cable to be constructed with a considerably smaller diameter and cross-sectional area. The benefits of selecting a 200 micron fibre can be taken in several ways. Around a 30% increase in fibre density or fibre count can be achieved. A smaller cable diameter naturally translates to a lighter cable with a smaller cross-sectional area. More cable can be stored on a single cable drum, and smaller, lighter load can also deliver lower freight costs when transported to the site. The advantages of a smaller fibre delivering more compact and lighter cable seem so obvious, you may be wondering why the industry has standardized on the larger diameter for so long. In fact, this fibre type is the product of advances to both the glass and the coating components of the fibre. When deployed in a tightly packed cable, the signal carried by an optical fibre is very susceptible to loss through microbending. External forces, such as those created by fibres crossing or being pushed against the walls of the tubes, leads to tiny deviations in the optical core, causing light to be radiated out of the fibre. The coating provides some level of buffer against these forces. If the thickness of the coating is reduced, so the effectiveness of the buffer is reduced, and the 200 micron fibre would incur unacceptably large losses. This effect must be mitigated by the choice of glass design and coating. In part, 200 micron fibres are made possible by the use of bend-resistant fibre complying to the ITUT recommendation G.657. G.657 fibres are known primarily for their resistance to macrobending loss when constrained to bends of 10 mm radius or less. Their advanced glass design leads to more light being trapped in the core when tight bending is incurred. The glass properties that protect the fibre from excessive macrobending loss also deliver superior microbending capability. A standard G652D fibre would incur excessive loss in a constrained cable with the reduced thickness of coating. A G.657 fibre provides much greater microbending resistance, making the 200 micron concept feasible. The final protection against microbending loss is delivered by an advanced coating. Conventionally, optical fibres are coated with a dual layer of acrylate, a softer inner layer to provide buffering against external stresses, and a harder outer layer to provide protection against damage during handling and processing. The superior buffering properties of Corning's CPC coating system ensure that the microbending forces are successfully absorbed, even when the thinner layer associated with 200 micron fiber is applied. In fact, the buffering properties of the coating are so good that the fiber can be designed with G.657A1 compliant glass rather than the G.657A2 compliant glass types that formed the basis of the earlier generation of 200 micron coated fibers. As we'll see, this provides the fiber with a compatibility advantage that can prove beneficial when the fiber is installed. In most installations, the newly deployed fiber will be installed alongside a legacy network of conventional G.652D fiber. G.652D fiber typically has a mode field diameter of 9.2 microns. G.657 fiber is generally designed with a smaller mode field diameter. This attribute tends to assist in increasing the bend resistance of the fiber. The nominal mode field diameter may be as low as 8.6 microns and still comply with the standard. When the two dissimilar fiber types are spliced together, this mismatch of mode field diameter can lead to difficulties for the installer. Splice quality is generally determined by taking an OTDR measurement and identifying the loss at the point where the splice has been made. The smaller mode field diameter of the G.657 fiber causes a higher proportion of light to be backscattered to the OTDR than is the case for the conventional G.652 fiber. When spliced together, the change in the backscatter properties of the different fiber types leads to a discontinuity in the OTDR trace. This may be misinterpreted by the installer as a bad splice that's creating a large loss in throughput power. In reality, this isn't the case. The throughput power is many orders of magnitude greater than the backscattered power, and the loss feature on the trace is just a representation of the changing backscatter properties of the dissimilar fiber types. Nonetheless, this has the potential for confusion in an environment where speed of completion of the installation is critical. In this event, the installation team would have to travel to the other end of the link, then fire the OTDR from the other end. In this direction, the light is returned first from the conventional G.652D fiber with the smaller backscatter fraction, then from the G.657 fiber with the larger backscatter fraction. So at the splice, the trace is directed upwards, which is often referred to as a gainer. The correct approach to determining the actual loss at the splice is to take the average of the two values from the bidirectional measurement. But making the measurement from both ends is time-consuming, and the disruption caused by MFD mismatch during installation may persuade operators to disallow the use of G.657 in their deployments. In the context of 200 micron fiber, we've seen that the use of a G.657 glass design is necessary to help overcome increasing microbending effects, which are imparted when using a thinner coating. MFD mismatch, therefore, might become a barrier to the widespread use of 200 micron fibers and the higher density cables that they enable. In response to the clear advantages in space utilization that can be achieved from a smaller diameter fiber and the need for backwards compatibility to the legacy network to simplify installation, Corning has recently introduced SMF28 Ultra 200 fiber into its product portfolio. This fiber is compatible to G.652D and G.657A1 and exceeds the macro bending requirements of the A1 standard at 10 mm radius and 50 nanometers by 50%. The nominal mode field diameter is at 9.2 microns, ensuring backwards compatibility when spliced into existing networks. And finally, the fiber incorporates low loss, 0.32 and 0.18 dB per kilometer attenuation at 1310 and 1550 nanometers respectively. With this innovation in place, Corning expects to see rapid acceleration in the deployment of high-density mini cables in access networks around the world. So, let's now return to the four competing considerations for operators planning to build out in the access network. The critical product attributes that address these concerns are space, compatibility, loss, and bend. Corning's SMF28 Ultra 200 addresses the four critical considerations for network operators planning to upgrade their access networks to deliver improved operation and services. These considerations are the need to use limited space available in the duct efficiently and promote faster, lower-cost installation, the need for backwards compatibility with the legacy optical fiber plant, the need to maximize subscriber coverage, possibly from a smaller number of central offices, and finally, the capability to utilize more bend-sensitive wavelengths above 1600 nanometers to support upgrade to higher data rates in the future. Let's now look at each of these benefits in more detail. To discuss the space benefits achieved by smaller cables through the use of SMF28 Ultra 200, let's consider a range of actual cable designs that have been developed and enhanced through the use of this innovative fiber. Corning's Mini Extend cable range is an established line of microcable products delivering fiber counts up to 144. The highest fiber count in the portfolio is illustrated here, an 8.1 millimeter diameter cable packed with 242 micron fiber. Corning has now introduced Mini Extend HD cables, which is specifically engineered to leverage the reduced diameter of SMF28 Ultra 200 fiber for greater packing density. With 24 fibers packed into 9 buffer tubes, Mini Extend HD provides 216 fibers in the same space as the standard 144 fiber Mini Extend cable. This represents a 33% increase in fiber count with no increase in cable diameter. Alternatively, the fewer buffer tubes now required to achieve the fiber count, 144 fibers can be housed in a cable of only 6.3 millimeters diameter. This illustrates two of the options available in Corning's new Mini Extend HD range of microcables, delivering higher density, lighter cables to access networks. Each product in Corning's Mini Extend cable portfolio offers significant improvement in fiber density versus traditional loose tube cable designs. Operators can choose whether to take this benefit in the form of a higher fiber count for maximum data carrying capacity, or a smaller, lighter package for improved scalability and faster, cheaper installation. Using SMF28 200 fiber and Corning's Mini Extend HD cable range extends microcable fiber counts up to 288, all contained in a package that's less than 10 millimeters in diameter. Note in particular the reduction in relation to microduct diameter. Microducts are miniaturized plastic conduits which can be used to subdivide internal duct space and facilitate the installation of microcables to ease the problem of congestion in legacy duct infrastructure. The popular 1210 microduct size is now capable of being filled with a 216 fiber count high-density microcable, representing an increase of 33% from the 144 fiber standard microcable with conventional 242 micron fiber. The improved utilization of the duct infrastructure allows an access network to be built that can handle increased data demands from subscribers for longer periods before disruptive civil engineering work is necessary to install new duct infrastructure. As we've seen, microcables are a relatively new innovation. Much of the current access infrastructure consists of much larger traditional loose tube cables occupying a large proportion of the cross-section of the duct. In the restricted space available, any loose tube cable that's successfully overpulled alongside a legacy cable is likely to have a relatively low fiber count. The process of overpulling poses a risk of damage to both the existing cable and the new cable. However, the emergence of microduct and microcable provides the operator with an attractive alternative to simply digging up the road and installing new duct, always an expensive and disruptive option. A 1210 microduct can be blown safely into the occupied duct with its light weight representing little risk to damaging the existing cable. The space in the microduct can now be filled to extend the network capacity. The high-density microcable option containing 200 micron fibers delivers the most attractive and long-lasting solution. Whereas the standard Mini Extend cable allows the duct capacities to be doubled, the 216 fiber Mini Extend HD increases the capacity by 133% allowing the operator to extend the lifetime of the current infrastructure even longer. Incumbent network operators are often obligated by their regulator to share their duct infrastructure with alternative operators. The incumbent may charge rental for the use of the duct, the charge being determined by the regulator, and may be based on space taken up by the cable of the alternative operator. Alternative operators can lower their duct leasing costs by using 200 micron enabled smaller diameter cables. This provides a lower cost per bit for the alternative operator, a faster return on their investment, and hence an environment where the subscriber can have more choice in the provider of his broadband services. Smaller, lighter cables provide a host of benefits between leaving the factory and getting deployed in the field. Smaller cables can be placed on smaller drums without any loss in fibre density. This can allow more drums per wagon, lowering the freight costs. Once arrived at the installation site, the drums will be lighter and so easier to handle and quicker to load into position. And the lighter cables can be blown further at faster speeds. Alternatively, they may be blown into already restricted duct spaces or more tortuous routes, where larger cables would need to be pulled or may not be installable at all. SMS28 Ultra 200 is designed with a 9.2 nominal mode field diameter, which matches the legacy install base of G.652D single mode fibre. So when a splice is made and tested by OTDR, the backscatter fraction of both the new and the legacy fibre is the same. The effects of losers and gainers is removed, and the installer can tell immediately if the splice he's made is a good one or not. It's also important to remember that the 200 micron fibre is designed with the same 125 micron glass diameter as legacy installed fibre. This means that the smaller fibre type is still compatible with existing equipment and processes for splicing and connectorization. Now let's look at the benefits provided by a fibre with low loss in the outside part of the access network. Here the advantage is in increased subscriber coverage from a single central office. Attenuation of 0.32 dBs per kilometre at 1310 nanometers provides about a 10% improvement in reach compared with a conventional single-mode fibre with attenuation of 0.35 dBs per kilometre. This allows more outlying regions to be reached from a particular point, with the area of coverage increasing by about 20%. This capability reduces the occurrence of so-called not spots, suburbs which cannot be supported with a high-speed broadband rollout. A stated objective of a number of major operators is to be able to consolidate transmission equipment in a smaller number of central offices, delivering operational savings from the closure of redundant buildings and the potential for income derived from the sale of assets. In the above example, the closure of Central Office 2 would lead to a generation of not spots if the access network was built out with conventional fibre. With low-loss fibre, the outlying suburbs can all be met from Central Office 1. As Internet applications continue to expand, it seems inevitable that operators will, in the near future, have to squeeze more capacity out of the fibre plant they select to install today. This will mean migrating operations to new parts of the spectrum, and in particular to wavelengths below the current O band around 1310 nanometers and above the C band around 1550 nanometers. In fact, with next generation PON, 10G PON, WDM PON, the industry is already identifying the operational protocols that will prevail in the future, and the implications of those upgrade paths can be readily predicted. Consider the spectral attenuation of a traditional G.652D single-mode fibre. At the shorter wavelengths, below 1310 nanometers, higher attenuation is encountered, a trend that's controlled by the laws of physics. The deployment of a fibre with low loss can make the upgrade to higher capacity through shorter wavelengths more achievable. As you can see, the lower loss of SMF28 Ultra 200 fibre is delivered across the spectrum, so that when protocols are adopted that move upstream transmission to shorter wavelengths, the lower loss fibre will continue to support the reach achieved today at 1310 nanometers, whereas conventional fibre will be more restricted. So the selection of a lower performing fibre today can create challenges to the power budget in the future, leading to the need for fundamental changes in the network architecture and all the capital expenditure associated with that. Now, let's consider the impact of extending operation for downstream transmission to longer wavelengths, beyond the conventional C-band around 1550 nanometers. Here, the limiting property of the fibre is the bend resistance, since the longer wavelengths of the fibre become ever more sensitive to bending effects. In this example, we had 10 turns of 15 millimeters radius. That's the least constraining condition added to the G.657 standard for defining bend-resistant fibre. Even this moderate addition of bending results in a severe enough attenuation response from the conventional G.652D fibre, more than enough to prevent upgrade to longer wavelengths at the top end of the C-band. In contrast, not only is the SMF28 Ultra 200 fibre lower in attenuation throughout the operational spectrum than its conventional counterpart, the fibre is resistant to incremental bending that may be incurred in the outdoor access network. Indeed, you can see that the bend resistance extends beyond the C-band and out into the L-band above 1600 nanometers, when next generation PON and WDM PON are designed to provide an upgrade path for high-speed broadband networks. In conclusion, Corning presents its latest optical fibre innovation. SMF28 Ultra 200 is the first product to combine G.657A1 bend capability, low loss, and a mode field diameter that matches the legacy network, all in a smaller 200 micron package to deliver high fibre density installations in the outdoor access network. Thank you for joining this webinar. I'll now hand back to Tim and answer some of the questions that have been posed during the presentation.
Well, thank you very much indeed, Ian, for that presentation. Now, as I mentioned earlier on, we do have some time for Q&A. To submit a question at any time, just type into the comments box on this page, and Ian's answers will appear as text in the comment stream. There is no audio element to the Q&A, just a reminder. So it just remains for me to thank Ian and Corning for making today's Telecoms.com Intelligence webinar possible, and to thank everyone indeed who joined us for the presentation. I hope you found it useful, and please do look out for upcoming webinars that will explore other key topics affecting the telecoms industry today. See you again next time. Bye bye.